Hello and welcome to another video presentation on the second most important derivation to be studied by every 10th standard student. And this is the angle bisector theorem. Now in geometry, the angle bisector theorem is concerned with the relative lengths of the two segments that a triangle's side is divided into by a line that bisects the opposite angle. It equates their relative lengths to the relative lengths of the other two sides of the triangle. A very complex statement, yet let's try to understand this in a little more simpler way. The bisector of an angle divides the side opposite the angle in the ratio of the remaining sides. Let's try to understand this. Now we can look at this diagram and we can understand that we first of all have the main triangle ABC. And this ray CE is the bisector of this angle ACB. What the statement says is the bisector of an angle of a triangle divides the angle here in the ratio of the remaining two sides. And therefore you look at this to prove, we are proving that the ratio of AE upon EB is equal to AC upon CB. But then we have a question, why this extra? This extra is going to be used as a part of our construction, and we're going to use this in our very own derivation for this theorem. But before that, let's understand what the given has to talk about. And the given states that in triangle ABC, the bisector of angle C intersects segment AB at point E. But there is something even more important, the construction. We are drawing a line which is parallel to CE, and that line is DB. We are then extending AC to point D and meeting them where they intersect. Okay, now what we have concluded here is that these are our two parallel lines in the construction. There's no conclusion, it's actually what we are trying to use from the construction. Two parallel lines with the extension, and I would always, as previously said, in brackets, as shown in the figure, a little good formality to mention. Now, in order to understand this derivation, let's start. Ray CE is parallel to ray BD. Let's mark it off. Ray CE is parallel to ray BD, and AD is the transversal. This obviously we know that CE is parallel to BD from the construction, but as this is the transversal, we get that angle ACE, this angle, and this angle are corresponding angles. Now, if I turn and I use, instead of CAD as the transversal, I'm going to use BC as the transversal, I get this angle, angle ECB, is congruent to angle CBD by the alternate angles. So we got first this one and this one. Now we are getting this and this. Now there is another thing, that we've got angle ACE and angle BCE both congruent, obviously, which is given as the other bisectors. Therefore, we can conclude that this and this are equal because of 1, 2, 3. Repeating it again, I'll just erase what we have just marked it off precisely and use some different colors to make some nice distinctive explanations to the same. We got this angle and this angle equal by corresponding angles. We then got this angle and this angle equal by alternate angles. We already know that this and this is equal, and we can therefore conclude that this and this become equal. Now, obviously, we know the property of an isosceles triangle. If these two angles are equal, but obviously the sides opposite the angles will be equal. So using our existing knowledge about in geometry, we can conclude that side CB is equal to side CD. That's what's here. CB equals to CD. Now, if you look at this triangle as a whole, and we have got this parallel to this. By BPT theorem, AE upon EB is equal to AC upon CD. In case you do not know the BPT theorem, watch my previous video on the basic proportionality theorem. And that's what we've just got from the basic proportionality theorem. But since I know that CD can be replaced by CB from number 4, we then get the conclusion as this final statement, and we have hence proved what we need from this derivation. And in that way, we have concluded our basic proportionality theorem, in which we have got AE upon EB is equal to AC upon CB. Now, in order to understand this a little better, I have taken up a numerical in triangle MNQ, where NQ is the bisector of angle N. We have got MN as 25, PN as 40, MQ as 14, and QP is something that we need to find. I have used a little different numbers in 2 different ways. You can try it out with these numbers as well. But yes, when we are doing this, obviously I would give you a hint. It's always the 2 big sides, one upon the other, and then the 2 small sides, one upon the other. So you're like taking the numbers that are given in this diagram. Mn upon Np is equal to Mq upon Qp. Now Mn in this sum is given as 25 upon 40 is equal to 14 upon an unknown. And this is got by the angle bisector theorem. Cross multiply, x is equal to 14 into 40 upon 25. 5 5s are 5 8s are, and you can solve for and conclude your answer, which I would like you to think about and leave it with your solution rather than me teaching you how to go ahead with the calculation. In the next sum here, we've got LM as 6, MN as 10, TN as 8. Again, let's go with first the big sides, who are the non-bisector sides. That's LM upon MN is equal to LT upon TN. This gives us 6 upon 10, which is equal to X upon 8. For simplicity, I'll just reduce this down here right now. So I can get 3 upon 5. 3 upon 5 is equal to X upon 8. Therefore, X is equal to 3 into 8 upon 5. So 24 upon 5, and you can solve further for your conclusion in the calculation. With this, thank you for watching the second video presentation. Hope you like it. Please do like, share, and subscribe to our channel on both these videos on the 2 important theorems, basic proportionality theorem in the previous video and angle bisector theorem in this video. Thank you.